Good afternoon, everyone. I welcome all the viewers of the first Dr. Arvind Bhatnagar Memorial Lecture, which is being organized as the 16th Vyakyan in the series of 75 online Vyakyan or lecture series being organized by the Physical Research Laboratory as part of our Platinum Jubilee celebrations. On behalf of Director PRL, Dr. Anil Bharadwaj, my colleagues from the Udaipur Solar Observatory, and also on behalf of the Amrit Vyakyan Committee of PRL, I extend a very warm welcome to Professor Sami Solanki, who is the Director of Max Planck Institute for Solar System Research in Germany. And we are very honored that he will be delivering the first lecture of Dr. Arvind Bhatnagar Memorial Lecture on a very fascinating topic, that is the sun's magnetic field and global climate change. Thanks, Professor Solanki, for gracing this occasion in our Platinum Jubilee celebrations. Today's lecture is very special indeed, and it has been organized to remember and celebrate the achievements of Dr. Arvind Bhatnagar, who was the founder of Udaipur Solar Observatory. In fact, he established this observatory in 1975. We are also very pleased to especially welcome his family. I hope Mrs. Chitra Bhatnagar has joined us, and his daughters, Anita, Tripti, and Malvika. Very warm welcome to you and greetings to you all. It is my honor and privilege to say a few words about Dr. Arvind Bhatnagar today. I would like to share some slides just to, give a glimpse of whatever he did. Let me just share the slides. Can you see my screen?
Yes.
Yes. Okay, so Dr. Arvind Bhatnagar was born in Byawar, Rajasthan on 19th November 1936. After completing his MSc in physics, he joined the UP State Observatory in Nainital in 1958 and worked there until 1961. He was awarded a PhD degree in solar physics on the topic of evershed effect in sunspots in 1964 from Agra University while working at the Kodaikanal Observatory under the guidance of Professor M.K. Venubapu. Subsequently, Dr. Arvind Bhatnagar was awarded the Carnegie Fellowship to work at Mount Wilson and Palomar observatories during 68 to 70. And afterwards, he worked as a resident astronomer at the Big Bear Solar Observatory of the Caltech in US till 1972. Then in 1972, he returned to India and tried to establish the unique island solar observatory in the middle of the Lake Fateh Sagar. The pictures you are seeing as it stood at that time under the aegis of Vedshala, a private trust of Ahmedabad. This was inaugurated in the presence of the chief ministers of Gujarat and Rajasthan. And this lake site was actually selected by him after careful considerations of the fact that Udaipur has large number of clear days and large body of water is there to help the stabilization of air turbulence near the ground, which causes problems in observations of the sun. And due to his untiring efforts, he led to the establishment of the Solar Observatory and affiliation of the same with the PRL DOS in 1983. This is a picture of the event under which you see that Dr. Satish Dhawan, who was the then chairman of ISRO, he was very instrumental in transition of USO to DOS on 23rd December 1981. And as I said earlier, due to his untiring efforts and his passion for observing the sun continuously, USO became internationally renowned as one of the major centers for high resolution solar observations. And following the discovery of solar oscillation in 1970s, he understood it, and it became very evident that helioseismology could be used as one of the powerful tools to unravel the interior of the sun. For this, he led an Indo-US project from 1986 to 1991 by National Science Foundation, under which Udaipur Solar Observatory participated in the site survey program, and finally it was selected as one of the six observatories located on the globe of the network called Global Oscillations Network Group. And basically the idea was to study the solar interior. This is pictures of these events, and USO and GONG have a long-term partnership, scientific partnership with NSO. Here are the two main PIs from US side, Dr. John Liebacker, and from USO, Dr. Arvind Bhatnagar led this project. These are some of the other pictures of this event. So we are very happy to announce that GONG instrument has completed about 25 years of operation last year, and there was a small workshop on that particular occasion. In fact, Dr. Bhatnagar was the first one to realize the importance of the study of helioseismology, and he organized the first helioseismology workshop at PRL in January 93. You can see a picture that was done in PRL main campus in Ahmedabad, and subsequently small groups in various places in India, like USO, IIA, TIFR started working on helioseismology problems. So coming to his publications, he has about 80 publications to his credit, and he has worked on a variety of problems, starting from eruptive phenomena of flares and eruptive prominences, and also on helioseismology. He has produced a photographic atlas of observations from Udaipur, which is compilation of the data from 76 to 84, and he wrote a book on a very fascinating book on fundamentals of solar astronomy in 2005. His main achievements: Professor Bhatnagar was elected a fellow of the National Academy of Sciences of Allahabad. He was also a founder member of the Astronomical Society of India and a member of the International Astronomical Union. As many of you may be knowing that he was the founder director for Nehru Planetarium at Mumbai, but many of you may not be knowing probably that he was also instrumental and advisor to several planetaria in India, including Nehru Planetarium Delhi, Sardar Patel Planetarium in Baroda, and Jawahar Planetarium Allahabad. So this is an news which I gathered from some archive published in December 31, 1976, wherein he, while in the function of inauguration of the planetarium, he mentioned that it is a fitting memorial to the memory of the late Prime Minister Jawaharlal Nehru. And he actually said that coming back to India has been a challenge, and that too because of the tight economic framework that he had to deal with. But in spite of all these problems, he mentions that this is a very good attempt, and especially for nurturing love for sciences in the minds of our children. He even made free viewing for poor school children and fixed a very low minimal rate for viewing for adults and child who were school going. So there was loss for the planetarium, but he in fact was demanding the money for this kind of aid to come from the center. So this shows his passion for observation and popularization of solar astronomy. One of the adventures he did was to make an attempt that was supervised by him with a MiG-25 pilot of the Indian Air Force to observe the corona during total solar eclipse of October 24 in 1995 from a height of 25 kilometers with a speed of Mach 2. And this is again a newspaper clipping that I got in the recent times during the annular eclipse that occurred in December 2019. And people quoted this attempt because it was going to be repeated in this in the recent eclipse. He has also worked for social causes. He was very much committed to the beauty and protection of the environment near Udaipur, which is very beautiful and also has the city, and also called the City of Lakes. He started a novel project called Sushi, which is Swachh, healthy, urban, clean and hygienic environment in several localities of Udaipur under Astha for solid waste management through public participation. And for this work, he was also appointed as one of the High Court commissioners to monitor the directives of the High Court in connection with the protection of the lake system of Udaipur. I think he has a lot of interest. He had a lot of interest in the public interest work, and that he started to do after his superannuation. I think anybody who knows him would remember him as a very passionate, dedicated, and committed person, and that commitment was very infectious. In fact, he was able to enthuse both young and old alike with the excitement of observations, not only about the sun, planets, and stars, but also he would go for bird watching, for example, and he took me along with his daughters to watch flamingos. These are the migratory birds that come during winter in Udaipur. And so I think he was truly a very gifted and very keen observer. And to honor his contributions to solar physics and to the society, the Dr. Arvind Bhatnagar Memorial Lecture will be organized every year. And I'm thankful to PRL Director for initiating this organization of the lecture series and making it a part of PRL Ka Amrit Vyakhyan in this year. We are very honored and happy that the first memorial lecture in the series will be given by Professor Sami Solanki, Director MPS, who himself is a renowned solar physicist. I now invite Professor Shibu Matthew to formally introduce Professor Solanki and invite him to deliver the memorial lecture. Professor Shibu Matthew, please.
Yeah. Okay. So let me take a few minutes to introduce the speaker today. So Professor Sami Solanki is a solar physicist and stellar astronomer. He is director at the Max Planck Institute for Solar System Research in Germany. He did his PhD at the Swiss Federal Institute of Technology in Zurich. He was endowed with honorary and distinguished professorship by the same institute and also by the Technical University of Braunschweig and Gyeonggi University in Korea. He also received a honorary doctorate from Finland. He received a number of prizes and awards, such as, to name a few, Advanced Grant of the European Research Council, the Julius Bartels Medal of the European Science Union, and the Distinguished Scientist Award of Scientific Committee of Solar Terrestrial Physics. He has published more than 500 refereed scientific papers with more than 36,000 citations and an H index of around 98. So he's the founder and person of the International Max Planck Research School on Solar System Science. He's produced almost like 200 successful graduates, majority of which are still in science, including many now in positions like in permanent positions like professors and other positions. So he also founded the journal Living Reviews of Solar Physics, and he is the editor-in-chief of that journal. This journal is having an impact factor of around 20. So he leads the Sunrise mission, which is solar mission of the German space agency, along with NASA and Spanish space agency as the partners. And he is the principal investigator of polarimetric and heliospheric imager instrument on the Solar Orbiter space mission, and also co-eye of a number of other space instruments. With this brief introduction, I invite Sami for the talk, today's talk.
Yeah, thank you very much, both of you, for this introduction. First of all, for the introduction of Arvind Bhatnagar, one of the great Indian solar physicists. Nadita, thank you very much for telling us more about it. I learned a number of things I didn't know. And it's absolutely a huge pleasure and honor to be invited to give this first lecture of the series named after Arvind Bhatnagar, which I think is extremely deserved. He built up what is the prime solar observatory in India and has been a big force in lots of different initiatives. And thank you, Shibu, for making me blush with all the nice things you have been saying. I would like to tell you something about the sun's magnetic field and global climate change. It will be more about the sun and less about the climate, but the sun obviously does influence climate in some ways, and I will try and say a little bit about that. If you, oops, I have to, let's see, okay. So many astronomers, if they are asked to say something about the sun, they will say, it's a reasonably boring star. And compared with lots of the stellar or extragalactic objects that are studied by astronomers, it is a little bit of a boring star. And if you look at an image of the sun taken here with a small telescope in white light, it doesn't really look that terribly exciting, to tell you the truth. Things change if you zoom in, and we're moving towards that little sunspot on the side, and at the same time allowing the image of the Earth to zoom as well, so that we have roughly an idea of the orders of magnitude of the sizes. And while we're zooming in, we also change the telescope to a bigger one so that we can see a lot more structure on the sun and the dynamics. This other telescope, the SOT on the Hinode spacecraft, by the way, has the same size as the MAST telescope at Udaipur. Some of these structures that we see, so you have the sunspot in the middle. Let's see if I can run this again. Uses to run again. Okay, sorry about that. So you have the sunspot in the middle, and outside the sunspot, we saw lots of individual granules. These are convection cells where hot gas rises up, radiates away the energy it is bringing, and then sinks down as cool gas in the surroundings. One of these granules has a size of 1,000 to a few thousand kilometers. That means not so terribly different than the size of India. The difference is that one of these granules lives for around 5 minutes, which just shows how dynamic things are on the sun. We see a lot of other structure if you look at the sun in different radiation. So in the movie on the lower left, we see gas at around 10,000 degrees. This is just a small part of the sun that we see here. The edge of the sun is this dark line, which I will try to, I hope you can see my pointer. So that is the limb of the sun, that's its edge. And what we're seeing above it is the atmosphere. There is a prominence there. There are so-called spicules, little jets of material shooting out there. And then this is probably coronal rain material that is falling out of the sky. So again, extremely dynamic, very different structures than what we saw before. However, so far, everything has been sort of everyday. But from time to time, the sun produces a really spectacular display, as we are seeing in the movie on the upper right. This was a so-called coronal mass ejection, where the sun actually tries to throw out a part of its atmosphere. In many cases, that is successful. In this case, it's not completely successful. So you see a part of that gas raining down again. The temperatures that we are seeing here are between roughly 100,000 and 1,000,000 degrees. So the darkish, reddish stuff is around 100,000. The more white, bluish material, that is more 1,000,000 degrees. So yes, the sun can be nasty from time to time, because if one of these coronal mass ejections comes and hits Earth, it can have negative effects, in particular on sensitive technological equipment that we have, but can go all the, I think India is relatively safe being at low latitudes, but countries at high latitudes, it can even lead to loss of power, whatever. Now, basically everything that I've shown you so far and a whole number of further phenomena are put together, bunched together under the name of solar activity. And all of that is driven by basically a single quantity, and that's the magnetic field of the sun. Unlike the magnetic field of the Earth, that of the sun is extremely complex at the surface and in the atmosphere. There is some kind of dipolar structure, as you see from the field lines on the left, but there is also a lot of other structure. We also see that the magnetic field is connected with the very hot outer atmosphere of the sun, of the million-degree corona. In the movie that's running in the middle, yellow and blue are strong magnetic fields measured at the surface of the sun, whereas the white curved lines or loops connecting these two opposite magnetic polarities are basically gas at 1 million or more degrees. And from this movie, you see immediately that this hot gas is connecting the opposite polarity magnetic fields. It looks like you had a bar magnet lying there, and you put iron filings around it. You see a very similar structure. So the outer atmosphere of the sun is basically a magnetosphere. You again see these hot loops in the upper right image. One thing we learned, and we see a little bit of that if you look at this image here in the middle, the magnetic field is broken up into smaller and smaller pieces. And if you do an analysis of that, you will find it has something like a fractal structure. That means irrespective of what scales you're looking at least above a certain size, above the diffusion limit in the plasma, you will start to see smaller and smaller structures. And we have realized that a lot of the action is actually going on at these really small scales, where things move much faster and a lot more happens than at large scales. Unfortunately, it is not easy to observe these small scales. With small scales, I'm talking of a few tens to a couple of 100 kilometers. That is, of course, large on human dimensions, but small compared with the diameter of the sun, which is 1.5 million kilometers. Now, there are different ways of trying and resolving these small structures. One of the techniques to do that is to build bigger telescopes with ways of trying to reduce the effect, the blurring effect of the Earth's atmosphere. This is what is being done at Udaipur Observatory, where a very nice site was chosen by Arvind Bhatnagar, and where Shibu has been working hard to install a bigger telescope, more powerful telescope. You can do a lot like that, but you're obviously always going to be limited by the fact that you have the Earth's atmosphere in the way. The ideal is to go out into space where you're completely above the atmosphere. But that's also very expensive to bring a large telescope there. So we chose something in between. That is, we built a larger telescope than, at least solar telescope, than has ever flown in space or actually ever left the ground. And we decided to fly it from a stratospheric balloon. And here are some pictures. If you look at the upper left, you see the trajectory. We had 2 flights of this, both starting in Kiruna, which is in northern Sweden. It's above the Arctic Circle. And the nice thing is, in summer, if you send the balloon up into the stratosphere, that means to a height of around of over 30 kilometers, there is a steady wind that will take it towards the west, and you can bring it down over northern Canada. In principle, you could let it go around the world, but then you run into some other problems, more of political nature rather than natural causes. It takes about a week, so you have a week of uninterrupted observations of the sun, since you are In summer, above the Arctic Circle, you see the sun day and night. And so there is a good chance to get lots of perfect data. Here is a movie showing the launch of the first of these. The balloon has about nearly a ton of helium in it. The balloon itself weighs another half ton or so. That has enough rising power to lift up the 2.5 to 3 tons payload that we have underneath. Here you see the balloon rising. Actually, everything above that little red part over here, this is all balloon. It's being held together here because you don't need to let the helium expand in the dense lower atmosphere. When it reaches the stratosphere, the balloon will have a size with a diameter of around 130 meters, which is big enough to fit in the largest plane or have a football field. I don't know, cricket boundaries might be a bit short, but you could probably fit in a cricket field there as well. The rest is a parachute, and then there is a ladder that's just basically ropes which are holding the observatory here. We want to be really, really precise, right? We want to resolve things at a resolution, because we're observing also in the UV. You can do that with a 1 meter telescope of down to 0.05 arc seconds. That means you have to be really careful with the launch. If that thing hits the crane that is carrying it at the launch, then definitely you're not going to be adjusted anymore. But the people who did this is the NASA Columbia Scientific Ballooning Facility. They did a fantastic job. This thing rolls up, it rises for around 2 hours, and then it's in the stratosphere. After that, the winds carry it to the west. Okay. There have been lots of publications, way over 100 publications in refereed journals coming out of this. But I just want to show one result. I told you that the outer atmosphere of the sun has a temperature of over 1 million degrees. The surface of the sun has a temperature of less than 6,000 degrees. So that means there has to be some heating mechanism to get this outer atmosphere that hot. Remember, there is a huge oven in the center of the sun, but we are going further away from this oven, from this heater, and so temperature should be dropping, which happens all through the interior of the sun and to the lower atmosphere, but then it rises again very steep. In the meantime, we know it has got something to do with the magnetic field, but there has been no clear evidence of what actually is causing this heating. And there were two main mechanisms. One is braiding of field lines proposed by Gene Parker, and the others were different types of MHD waves, which were proposed even earlier. Now, if you look at a region where you have lots of magnetic field, and this is shown on the left, this is part of an active region. You're seeing mainly one polarity, the negative polarity, which is black here. White is the opposite positive polarity. In the other image, we are seeing coronal radiation coming at around 1 million degrees. So this is from the upper atmosphere overlying this, the surface of the sun, which you see on the left. And we are seeing only a small part of the big image on the left. These are data taken by the Solar Dynamics Observatory, which is a NASA spacecraft providing the up-to-date magnetograms and coronal data at a resolution of about 1 arc second. If you look now at the same region again with the magnetic field measured by the Sunrise Observatory, we change that on the left, you see immediately that we have a lot more structure. Of course, we have more than 10 times better resolution. So that's not unexpected. But what was unexpected is that we also see, besides this dominant, you just see this black polarity here, and you see this white polarity here, and they are mainly separated from each other. But if you look at high resolution, you see a lot of little white stuff just around the black polarity. Here again, here again, here again. Here you have mixed polarity, etc., etc. It's all over the place. And so Pradeep Chita, who is a senior postdoc at my institute, he did his PhD at IIA in Bangalore some years ago. He came up with the suggestion that what's going on here is that these coronal loops, which you had seen in a movie earlier, and you also see in this image over here, lots of those, that they are not just simple structures which are connecting one magnetic polarity with the other, but actually, at least at one of the foot points of these things, you have opposite polarities which are interacting, leading to jets. And we actually saw these jets in the sunrise data of jets of material shooting up and filling up this loop with hot material which is being heated by the magnetic reconnection happening in the low atmosphere at the foot points. This was completely unexpected. It is sort of the third main idea on how to heat the corona, and with the upcoming Sunrise 3 mission and also other new instruments, we hope to be able to say more about that. So at the moment we are preparing for, oops, sorry, I forgot to update this slide. This will fly in 2022, my fault. It was originally planned for 2021, but we are obviously there and didn't fly this summer, so it has to be 2022. The difference of Sunrise 3 to Sunrise 2 is that we have a new gondola. That is the structure. If you can see that in this image on the right here, it is the structure which houses the observatory, which houses the telescope and the post-focus instruments. So it's much more stable than the one we had before. And we have a bunch of new instruments, in particular also upgraded instruments. And the difference, there will be many new things we can do. But one new thing is, oops, I need to go here again. Yeah. One new thing is that whereas with Sunrise 1 and 2, we were very much limited to the lowest part of the solar atmosphere that we could image or observe. Now we are looking at a much larger part of the atmosphere. In principle, we can also look a little bit deeper into the sun. So we are covering not just the photosphere, but also the whole chromosphere this time. Okay, so let's move on. Now I pointed the importance of the very small scale structure, which is important for making things happen here and now, and are responsible for a lot of the physical effects going on in the solar atmosphere. If you look at longer time scales, there is another feature which is really striking, and that is the activity cycle of the sun. And it's almost irrespective of which variable you look at, you will see that it changes, things change, whichever phenomenon. For example, here you see X-ray emission of the sun. Now, these X-rays, they're showing you gas at 3 million degrees or more, so they're really the hot part of the corona, and it's extremely variable. So each image is taken 1 year apart, and if you start in the first year, you see the sun is very bright in X-rays. As you go a few years later, this brightness has disappeared, and it is a factor of 100 less bright at activity minimum. And if you wait a few more years, it comes back to its original brightness, a bit less, a bit more, depending on how strong that cycle will be. And this cycle is repeated. You can look at sunspots, you can look at faculae, prominences, flares, whatever, shape of the corona, whatever you want. You see it repeated in just about every observable. It has a length of roughly around 11 years, but it's a cycle, it's not a periodic thing. The magnetic field also changes, and it's clear that this variation over the solar cycle is being driven by variation of the magnetic field. Now, I don't have time to go into talking about the dynamo of the sun, which is producing this magnetic field, but the dynamo we know is there are different models around there, and they do not everyone agrees which one is correct. So we need to find more observational evidence for that. And one problem is, it's not the only one, but one of the issues for not understanding the dynamo is that, I'll just start that in a minute again, is that we have never been able to look down at the poles of the sun. And we know that some of the action, at least, is happening at the poles, because if you want to predict how strong the next cycle will be, pretty much your best bet is to look at how strong the magnetic field at the poles is in the previous minimum. That's one of the best indicators, if not the best, for the strength of the next cycle. So obviously the field, what is happening at the poles, is really driving the dynamo over a solar cycle. We haven't had any spacecraft with telescopes on it that went out of the ecliptic so far. So we know the equator of the sun pretty well. We know the poles very poorly. And this is something that the Solar Orbiter mission, which you're seeing in this movie over here, is going to change. Solar Orbiter was launched in early 2020. It's now at the end of its cruise phase, after which, so it has already done these rather, how should I say, unusual maneuvers, going further out than Earth's orbit. So what we are seeing here is the sun in the middle. Earth is this planet out there. Venus is the yellow one here inside, and the blue orbit is Solar Orbiter. It has passed by Venus, it has passed by the Earth, and then it goes into its final orbit, or close to its final orbit, because it will keep on having gravity assist maneuvers by passing very close to Venus repeatedly. And the beauty of it is that each time it does that, it goes more and more out of the ecliptic, which is given here by the orbit of Venus. And so it will start looking down on the sun. We have been involved in a bunch of instruments for that. Our main contribution, for which I'm the PI, is the magnetograph, which it's not clear what it will see. This is just a simulation based on observations of sunspots, active regions, and then we just let that run, or rather Karel Schreiber let that run, to produce what is happening at the poles. But since we know very little about the flows at the poles, this is very likely not to be correct. And this is one of the things that we hope to be able to solve with Solar Orbiter. So just like Sunrise 3, Solar Orbiter will start delivering its first data, the first real science data, next year. What is going to happen much before that, at the end of November, in just a few days down the line, is that Solar Orbiter is going to have its Earth flyby, going really fast, very close to the Earth. It will only be around 300-400 kilometers from the surface of the Earth. Everyone is terribly worried at the moment because, as you might have heard, the Russians just blew up one of their own satellites, which was at around that height. And so there are now thousands of pieces of space junk in that orbit, for which there hasn't been any time to work out where they're actually. So it makes the task of the people who are steering the spacecraft safely through all the other satellites and space junk that is known really difficult, because they don't know where the newest stuff is. But yeah, so in a few days, hopefully, keep fingers crossed that there will be no damage. All right, let me switch now from magnetic field to irradiance. They're not unrelated, as I'll show you in a minute. So total solar irradiance is the total brightness of the sun integrated over the solar disk. So everything sun seen as a star, but also integrated over all wavelengths. That means it's basically the complete radiative output of the sun. What you're seeing here is a measured time series put together from different instruments flying on spacecraft. You have to do it from space. The variations are too small to be able to reliably separate from atmospheric fluctuations when observing from the ground. And so first measurement started in 1978. You see it's very noisy. The different colors are just data from different instruments and different spacecraft. See, it's extremely noisy. It's solar noise. If you take the average, 81-day average over that, you get this curve here, which is following the solar cycle. So we see that, okay, just one, the solar cycle, I'll tell you that in a minute. I told you that the noise is basically solar. It's not noise at all. It's actually the sun changing. And you see that very nicely in this blow up on the left, where one of these dips, not a very big one here, happening at the end of 1996. And at the same time, you see images of the solar surface, where over this period of time, these 10 days where this dip occurred, you have a group of sunspots moving across the solar disk. The sun is rotating with a period of around 27 days. And so in about half that time, the sunspots move from one edge of the disk to the other, but because of foreshortening and limb darkening, you don't really see them the first and the last couple of days. So that is this dip, and it's sort of understandable, right? I put dark features on the surface of the sun. If they really block the energy moving out, then I'll get a reduction in the total brightness of the sun. The variations are small. We're talking here about 0.1%, right? This is much smaller than the factor of 100 that we had with the X-rays. But there is a lot more energy in this. Now, are sunspots the only cause for irradiance variations? Let's look at that. We just saw sunspots cause darkening. However, if you plot the irradiance now, not on a day-by-day basis, but take such an 81-day average, and you compare that with the 81-day average of the number of sunspots, which is plotted below in red, the irradiance is on the top in blue, you see they actually correlate and not anti-correlate. So something else has to be going on. Right? Sunspots are leading to a darkening. So there has to be something else going on in parallel, which overcompensates for the sunspots and leads to a brightening of the sun. We also know what that is, and these are the so-called faculae. So I have in this high resolution image over here, I have dark sunspots, but around them, I see lots of bright features, tiny bright features, but finally they are covering a huge area compared to the sunspots. And just as the number of sunspots increases from activity minimum to maximum and then goes down again, the number of these bright features, the faculae, does exactly the same. And over long time scales, because they live much longer than sunspots. And actually, when sunspots decay, they decay into these little facular features. Faculae win. And they are what is what are driving the irradiance changes on the longer time scales. We can model that using, and both, may I just come back again, sorry, both the sunspots and the faculae are magnetic features. If I had no magnetic field on the sun, there would be no irradiance variations, except very small fluctuations due to these individual granules due to the convection cells. So it's basically the magnetic field at the solar surface which is causing irradiance changes. You can test that by taking measurements of the magnetic field, replacing sunspots by dark features, replacing the other magnetic features by bright stuff like the faculae, using measured values for their brightness. And then you can compare You can calculate the irradiance that you would get or the irradiance change, and you can compare with the measured values. And you see that they agree really well. So I keep forgetting. Yes, red are the measurements, orange daily values, in red I think half yearly or yearly averages, running means, in blue the model. Light blue, dark blue, the same thing. Very similar. Yeah, so we can get the R square, that is the square of the correlation coefficient, is 0.92. Mainly that is at early times when the measurements were no good. If you look at the later times, since we have superior measurements, it's better than 0.95. That means you can reproduce 95% of all the variations, or more than 95%. Some is still noise, right? There is still noise in the measurements. It looks even more remarkable, this agreement, if you plot it as a power spectrum. This is a global wavelength power spectrum of basically the time series we saw here, actually going a bit further in time, starting a little bit later to have the more recent, the better measurements there. Here the colors are exchanged, forgive me. So blue are observations, red is the model. Here we do include also the convection, the granulation, so that we can cover 6 orders of magnitude in frequency, or period if you want, or 8 orders of magnitude in power. And the agreement is remarkably good over this huge range. Looking at it this way, we can also very easily distinguish which parts are dominated by which kinds of features. So at the very short time scales of a day and less, it's the granulation, it's the convection cells. They produce very little variation. You can see the power is very low here on the right, but that's dominated by the granulation. At intermediate times, right up to the solar rotation time scale of 27 days, sunspots are dominated. As you go to longer time scales, faculae take over and completely dominate, also at the 11-year period of the solar cycle. So we have understood reasonably well what is causing irradiance changes up to solar cycle time scales, maybe also a little bit longer. Certainly, we have to reproduce things on a longer time scale to be able to say if brightness, say, changes of the sun are affecting climate. Why do we think that that such changes could affect climate? That's because basically the sun is providing us with 99.96 something % of all the energy entering the Earth's atmosphere, entering the climate system. The rest is coming mainly from the Earth or cosmic rays and stuff like that. But otherwise, solar radiation is the dominant form of energy reaching us. If you change that amount of energy, you are at some level going to also change the temperature at Earth. That's why understanding this is important, especially because climate change happens often on very long time scales. So we don't have the measurements to do that, so we need models, we need an understanding to be able to reconstruct irradiance on longer time scales, although it is not trivial. So what information do we have on solar activity? We cannot compute, we cannot predict activity with great reliability for centuries in the future, and we cannot say what the sun was doing for centuries in the past purely from models. We need to have some observation. The longest direct time series we have is sunspot number, just counting the number of sunspots. This started in 1610, shortly after the telescope was invented in 1609, and has been carried out almost uninterruptedly for this whole period of time. You see the solar cycle very nicely. Every 10 to 12 years, you have a maximum, minimum, maximum, minimum. You also see that each cycle is unique. It can have a different amplitude, it can have a slightly different length, different shape from the others, etc. Unique fingerprint every cycle. There are also some special periods. For example, in the second half of the 17th century, from around 1640 to 1700, 1710 or so, there were basically no sunspots on the sun. This is not because people were not observing. They were very excited about sunspots. They had just been discovered a couple of decades ago. They observed, but they were very frustrated because there was hardly anything to be seen. Now, if by chance or not, that also happens to be this period called the Maunder minimum, also happens to be the coldest part of the so-called Little Ice Age. Now, I don't know about India, and I would guess maybe India did not suffer so much, but in Europe, certainly, the whole Atlantic, European part of the world was greatly affected by the Middle Ice Age. It was bitterly cold at that time. So you see a painting here by Henrik Averkamp, who is a Flemish, or was a Flemish master. Very typical for these Flemish winter scenes was frozen lakes and frozen grachts. Grachts are these canals they have in Holland and Belgium, and rivers where people were ice skating. It doesn't happen anymore. It was multiple degrees cooler than now at that time. It was bitterly cold. At least people were dying of hunger in Europe. It didn't help that the 30-year war was going on at the same time in Europe. Other parts of the world were maybe less affected. Again, there is another period around 1800 when the sun was rather inactive. This was another very cold period. It was the last time that the Thames, the River Thames, froze sufficiently to have a Christmas fair on it. You have to be careful there because, you know, in the meantime, there have been dams built, etc., on the Thames so that the water flow is different, and it's not clear if it would freeze if it would get that cold again. But it was cold. Again, that's a little bit of statistics, but probably not good enough to say if the sun actually is affecting it. We need to have a much longer time series than these 400 years of solar activity to have more such periods of time when it was particularly cold or particularly hot to see if the sun could have played with it. We don't have direct measurements. There are naked eye observations of sunspots, but they're very patchy, not very useful. But we're in luck. Nature provides us with natural archives in which solar activity is stored over thousands of years. And this has got to do with cosmic rays, high energy particles, usually very high energy protons traveling at near the speed of light, coming from outside the solar system, some of them the most energetic coming from outside the galaxy very likely. If they come and reach, some of them will reach the heliosphere, they will get into the heliosphere. Some of them will get into the inner heliosphere, and if they reach the atmosphere of the Earth, they will interact. Because they're going at such high speeds, they have a rather large cross-section for interacting with whatever is in the atmosphere. Usually it's nitrogen, sometimes oxygen. Argon, these are the three main constituents. And if they interact, the energy is so high that it's going to be basically nuclear reactions. So a nitrogen nucleus can be turned into a carbon nucleus, for example, but it will not be the normal carbon, which has 12 nucleons in it, protons and neutrons, but it'll be 14 because that's the number that nitrogen has. So we just turn one of the protons of nitrogen into a neutron, and then you get carbon-14, which is a heavy sort of carbon. It is also unstable. It is radioactively unstable. It decays with a half-life of a little bit less than 6,000 years. That's a very useful thing because you have carbon in all kinds of material, wood, for example. So if you can measure how much, so if I have a dead tree, I can measure how much carbon-14 is in there, and I know how much was produced at an earlier time, I can tell how old that tree is. Now, if the production is constant, that works very well. Unfortunately, the production is not constant. Well, unfortunately for archaeologists who need to date it, very fortunately for us solar physicists, because one of the main ways in which the level of carbon-14 production in the Earth's upper atmosphere is modulated is by the sun's magnetic field. So if we can find out how much carbon was produced at a certain time, we can tell how strong the magnetic field of the sun was. And from that, we can find out how many sunspots there were, etc., etc., because the magnetic field is driving all the other activity. For this, we need dating. If you have a dead tree, you need to know exactly when it lived. You have to go the other way to calibrate your carbon-14, which is what we need to do to get the solar activity. And you can do that over dendrochronology. If you have the tree rings, as you can see down here in the lowest image, the width, it's again like a fingerprint. And for a particular type of tree growing in a particular region, you can tell exactly when the tree lived, if it lived long enough so that you can get this fingerprint unique. So we can reconstruct, for example, the number of sunspots as a function of time. And here is one particular reconstruction. The first one we did was in the early 2000s, 2004, we managed to do a whole Holocene. Later on, we improved things, and we've been continuing to do that. So this is one particular reconstruction from 2007, where you see this is now averaged over about 40 years. So you don't have solar cycles in there anymore, individuals. They would vary very fast, right? This is going over 7,000 years. So there would be 700 of them roughly. So we have averaged this over 30, 40 years so that you see the larger term change. What do we see? We see that there were times when the sun was very inactive, sunspot number basically 0. The last of these was the Maunder minimum, which we also observed from direct sunspots. There were other such minima. This is called the Spörer minimum, the Oort minimum, etc. Some of them less deep, but there are also uncertainties. Of course, there are error bars on these reconstructions. There were also times when the sun was particularly active, which are marked in red over here. We call these, so the others we call grand minima, the ones which are blue. The ones which are red, we'll call them grand maxima. And the interesting thing was that the sun had a grand maximum just very recently. When we were doing this work at that time, the sun, we thought, is still in the grand maximum. In the meantime, it has come out of that. The solar cycles have been weakening since 1980, and now 24, 25 so far, as we can tell till now, are relatively weak cycles compared to what we were used to over the last 60, 70 years before that, but they're actually quite normal cycles. So we are back at an activity level, which would be here in this gray level here, which is what the sun spent most of its time. So we are back to normal. Now that we have a reconstruction of solar activity over a long period of time, one can compare that with various measures of, do you see the complete picture? Because I have the images of the people there. Is that okay? All right. Does it make a difference if I move this over here? I'm not sure. I don't have an experience with WebEx. Yeah. Okay. So if you compare that with measures of climate, we see that at least for certain of these, for a certain period of time, there is a correlation. You see another one here where you have a relatively nice correlation here on a much shorter time scale. And these are very, very different parts of the Earth: North Atlantic, Alaskan, subarctic. In Oman, on the Arabian Peninsula, you have correlations which are significantly higher than if it were just by chance. And so this suggests However, without having a clear mechanism, this suggests that on historical and prehistorical timescales, for the natural variability of climate on Earth, solar activity was playing a role. We also know that as activity changes, brightness of the sun changes. So very likely solar irradiance was an important player in affecting the climate on Earth on these prehistoric times. It's not the only one. Volcanoes played a big role. There is natural variability. That's why the correlation is also far from perfect. Noise also plays a role, of course, uncertainties, but it played a role. Right. Now, that has changed very significantly if we look at the recent past. The recent past is obviously of particular interest because that's where man-made greenhouse gases have been playing an increasingly prominent role in driving climate. This was not there before. That plus land use change by humans, both very important drivers. And so what we see in the last 150 years is this red curve here. This is an 11-year average. The actual measurements are the red ones there. Those are yearly averages. The thin ones, the thick one is the 11-year average. And you see there were two bursts of warming on the Earth. One was in the first half of the 20th century, and then a bigger one, which is continuing, starting around 1970 or so and continuing till today. In yellow is the total irradiance of the sun, the total brightness, as computed. My God, I'm already talking an hour, I think, yeah, or almost. As computed with the model, our satire model, which I showed reproduces the measurements extremely well. And you see that in the first half of the century, the two things were sort of running in parallel. So solar irradiance could have very likely did to some extent contribute to this first rise in temperatures. But then in the second half, since 1970 or so, there has been no increase. Actually, there is evidence that there is a decrease. There is, because the measurements here have been put together by, from different satellites. Cross calibration is always an issue. So there is some uncertainty there. Let's say, it could also have been flat, but it certainly hasn't been rising anywhere like what we have seen for the temperature. So there is obviously a decoupling in the last 50 years or so that even if the sun did play an important role in driving climate on prehistoric times, this coupling has broken down in the last decades. And there is no way of getting around it that man-made greenhouse gases, other human activity, have been responsible for this. I have more slides. I want to jump over this here. No, actually, I'm not going to jump because this has got to do with India. There is some uncertainty on the magnitude of irradiance variations. So our model, plus most other models actually, are giving a relatively small change in the irradiance variation. So that during the Maunder minimum, the sun was something like 0.1%, at the most 0.2% less bright than it has been in recent decades. There are, however, other models, the so-called Chronos models coming from Davos, which give a much, much larger decrease in brightness of the sun during the Maunder minimum. So here we have time, this being today, this being the Maunder minimum here when the sun was very quiet. These are typical models here, whereas these are the Chronos models, which give an order of magnitude difference. Not a very healthy state of affairs. We need to sort that out somehow, because if it is 0.6 watts per square meter, which is the smallest change given by models, that is not going to be it's going to play a very small role on climate. If it were 6 watts per square meter, which is what the strongest of the Chronos models give, that is going to have a huge effect on climate. The problem is that so far, if you remember, we have sunspot number data going all the way back to the Maunder minimum and beyond, but we actually have no other direct data, direct measurements of the sun. What we are missing are the faculae, the little bright guys. So we have the big dark guys, but we don't have the little bright guys. There is a chance of getting them, because for the last 130 years or so, there have been measurements of the sun, brightness of the sun, taken in light of calcium-2 lines, the very strong lines formed in the chromosphere, and their brightness reflects the brightness of these small-scale features, mainly of the faculae. So we would have the information there, not over the last 300 years, but at least over the last 120 years, and we could calibrate. And if you go back, you can see over, the models already deviate hugely over the last 100 years. So you can distinguish between, right? The trouble is that many of these measurements, they're old, they have degraded over time. There were problems with the instruments, which people didn't realize at that time, etc. So this is a plate taken from Kodaikanal, and you can't use it. This is not very useful. However, we have a postdoc now who did his PhD with me, very bright guy, Theochatzis Stergos. He did magic. He found a way of correcting this, and he has tested this using, independent data, modern data, which are degraded in a double-blind manner. He doesn't know what it is, and he gets the original back again really, really well. And so this is the same image after the correction. And now we are starting to reconstruct the irradiance using these data. There is still some way to go. It will be a work of a couple of more years. But I hope also thanks to the Kodaikanal data, not only, of course, there are many such data sets around the world. They get sparse as you go back. So you need to combine them all. And that's what he is doing to try and get the aim is to get a robust reconstruction of the irradiance. There is another issue. And that is, so far I've been talking about the total irradiance. What you see here is total irradiance. That's not all that's going on. If you remember, I told you in the beginning that at X-ray wavelengths, the irradiance of the sun, just the spectral irradiance at X-ray wavelengths, changes by a factor of 100 over the solar sun. Total irradiance changes by 0.1%. At wavelengths in between, in the ultraviolet, the irradiance can change by percents to few percent. So much more relative change than you have in the total irradiance. And that could be important because what is being plotted here is the height at which the Earth's atmosphere absorbs the UV radiation coming from the sun. So down to nearly 300 nanometers, it is absorbed very close to the Earth's surface, and it's never completely absorbed. You do get a little bit, a tiny little bit. This is what causes, sunburn if you're out in the sun. That is this long wavelength UV radiation. If you go to shorter wavelengths than that, below 300 nanometers roughly, the height at which it is basically completely absorbed goes up very fast, which is very good for us because otherwise we will all be dying of skin cancer. And the molecules that produce that absorption are mainly oxygen, nitrogen, nitrous oxides, ozone, with ozone being dominant at wavelengths longer than around 240 nanometers, oxygen being dominant at shorter wavelengths. For the climate on Earth, the part that is most interesting is between 200 and 300 something, 400 nanometers, which is mainly absorbed in the stratosphere. And the balance between ozone and oxygen is what makes the music. The advantage here is that if you have solar radiation at this wavelength, it's going to get absorbed up directly in the atmosphere. It will not come through to the ground and be re-radiated again, and then maybe part of it gets absorbed on the way out. Greenhouse gases play a role there, etc. But here the energy gets deposited already directly into the atmosphere. Otherwise, most of it is radiated away at night back into the sky. So that is one thing that is important. The other thing is that although the sun emits relatively little flux in the UV, only 9% of the total flux, the variability is really high. Anywhere from 30% to 120% of the variability of the total solar irradiance is being contributed by the UV. So the UV is extremely variable. It is getting absorbed directly in the atmosphere. So it's something we should study well. Unfortunately, again, there is a problem. And the problem is that, okay, this is just the UV part in the green. The problem is that there is a huge mismatch between models and observations as far as the variability of the sun in individual wavelengths is concerned. The total solar irradiance has been produced by our models beautifully. However, in the UV, we see that this is now not our model, NRL SSI. This is coming from the Naval Research Lab in the US. It has a smaller UV variability than we get by a factor of 2, but it shows it's minute compared to what you have from the observations from the SIM instrument on the source spacecraft, which gives more than 100% of the variation of the total solar irradiance coming from the UV. That is only possible because SIM says in the visible, the sun is actually changing in antiphase. It is darker at activity maximum. Now, Joanna Haig showed in a very influential paper about a decade ago that if these measurements are correct, the blue curve, then this would have a huge effect on the climate. Whereas the models say, yes, there is some effect of the UV, but it's nowhere nearly as large. We're talking of, also a factor of order of magnitude. The trouble is, of course, the models, there are no good data of how bright individual magnetic features are in the UV. There is some light coming down to Earth, but it's very little. The observations are miserable that you do on the ground. You cannot get that reliably because there's too much attenuation in the atmosphere. So the models have an uncertainty there, what's happening in the UV. Things could be different. Fortunately, also the observations have a huge problem. This is a spectrograph which has to run stably for a whole decade without any degradation. You can do that for total solar irradiance instruments. They're built totally differently. But for a spectrograph, this was the first one, SIM, that tried to do that. Also Solstice, but Solstice only looks at the extreme UV, but it's a little bit easier. SIM tried to do that over the whole wavelength range, and it's very, very tricky. And not everyone believes that those measurements are correct. We hope that next year, starting next year, we will be able to resolve this. And this is thanks to the Aditya instrument, to the Aditya mission to be launched next year by ISRO, which has an instrument on it, SUIT, the Solar Ultraviolet Imaging Telescope, where the PIs are Durgesh Tripathi for the science and Ramaprakash for the instrument. By the way, Aditya is also carrying a solar wind instrument, I think, which the PI is at PRL. So there is some relationship there. Now, the thing for Sud, the reason we proposed this to Durgesh to have such an instrument, I'm very happy that ISRO bought the idea and decided to do that, is that this will measure the brightness of the sun in different filters in the ultraviolet. So that, and resolving, not just sun as a star, which is what SIM was doing, but it's actually resolving the whole solar disk, where we can then determine the contrast of the various magnetic features. We will get the magnetogram from other instruments on the ground, Solar Dynamics Observatory or wherever, and we will then be able to determine the brightness of individual magnetic features in the ultraviolet, and hence calibrate the models for the UV, make them a lot more reliable than they are now. And then we will see if that changes things a lot, then it would mean things are like, the SIM measurements give. That means the solar UV would have a huge effect on climate, or they're more like the models suggest, then it would be a much smaller effect. So now I think I have talked for quite some time, and I want to, let's jump over that and basically just thank you for your attention.
Thank you, Professor Solanki, for a very insightful talk, both on magnetic field and its effects on climate. I'm sure there are so many questions for you, and you have a constraint of time. So without further this thing, I will ask Bhuvan Joshi to conduct the question and answer session.
Thank you. Yeah, thank you, Nandita. So thank you very much, Professor Sami Solanki, for this very intriguing and wonderful talk. So I'm sure that your talk must have generated curiosity and interest among our viewers who are watching us over the YouTube, and also within our panel of experts joining us through WebEx. So I'll directly go first to the questions which are there on the YouTube chat box, and then I'll come back to the panelist. So first I'll take question by Dr. Neeraj Rastogi. So he's asking, what are the benefits of balloon-based measurements over satellite-based measurements for studying the sun?
Right. There is one benefit, and only one. Well, no, there are two benefits. So the first one is cost. Mm-hmm. It costs more than an order of magnitude less to have a balloon instrument flying than to actually get something into space. The other advantage, there's a disadvantage that you have much shorter flight times, things are not completely stable. We have a very, very complex image stabilization mechanism on board to get the images stable, that you can get really sharp images. But the other advantage is, because your flights are short and you recover your payload, you can upgrade things. And this is what we are doing. Sunrise 3 will have much more advanced instrumentation than Sunrise 1 and 2. People had tried before us to fly large solar telescopes from balloons to get high resolution. They got observations, they were not high resolution because there are huge challenges in getting that stability. But now that we have proven that we can do it, we are now going to use instruments which are a lot more sensitive, both in the sense that you get more information. So we're using spectropolarimeters now, spectrographs with polarimetry and not just a magnetograph or images. You can get much more information, but they're also much more sensitive to things going wrong. These are the main advantages.
Thank you very much. There is another question by Dr. Rastogi. What parameters decide the cyclicity of 11 years?
Well, that's a very good question. I think different people will give you different answers to that, because for the dynamo, there is quite some controversy about where it is located, how it is exactly acting. If I take the conventional view, so there are different parameters which play together. But if I take the conventional view that the dynamo is located in the overshoot layer below the convection zone, it takes some time, because there is differential rotation there, to build up a strong toroidal field. Sorry, I didn't say anything about the dynamo, so this is coming out of the blue. To build up a strong toroidal field, this field will go unstable above a certain strength, something typically like 10 to the 5 Gauss or something like that. It takes multiple years, but not decades, to build up that kind of field. So it takes 2, 3, 4, 5 years. And that's sort of half of your solar cycle. The other parameter which plays an important role is diffusion and transport of flux to the poles by the meridional circulation. That again takes about 2 years for flux to reach the pole. You have to kill the previous opposite polarity flux that was there. That takes another few years. So you get another 5, 6 years for that. And then together, this gives you roughly the 10 minutes. But as I said, other people will give you other answers.
Thank you. Yeah, thank you very much. So there is another question by Mr. Suraj Sahu. So he's asking what factors decide the height of these magnetic field lines or loops?
So there are different factors. The main factor is how far apart the foot points are. And actually, if you look at the image that's just given here, you see there are very small loops which are basically given by the fact that the foot points are very close together. If I have the opposite polarity fields further apart, like here, you get higher loops, or if they're even further apart, I'll get even higher loops. And if they are so far apart that the solar wind takes over, I don't get loops at all. I get field lines that open up into the interval. So there are other factors, but that's the main.
Okay, yeah, thank you. So there is another question by Dr. Harish Gadvi. The question is there any modeling study that suggests sunspot can disappear in future also, like Maunder minimum period?
Oh, I'm sure there will be another Maunder minimum period. Yeah, if you look back at solar activity, as I said, over the last 10, 11,000 years that we could reconstruct the solar activity so far. And actually, I have seen some data taken from trees which were living during the last ice age, the younger Dryas, which was sort of the last separate little tiny ice age after the end of the main last ice age. And there were evidence there that probably the sun had another grand minimum, at least one in that period of time. Statistically, they happen every 1,000 years or something like that. They come in bunches, and we cannot predict. So yes, there could be one happening anytime, or it may take many hundreds of years for them to come.
Yeah,
actually, it's less than 1,000 years. I think it's every 400 years or so.
Yeah,
but it's not periodic.
So I'll take another question now by Professor Bhandari. So the question is, are there any observational evidences of some Maunder minimum effects on planets like Jupiter and its satellite, or for that matter on Mars, etc.?
We would have to have a reconstruction of climate on these planets. Yeah, I don't think observations were good enough to say that. Maybe on Mars, if you get, I don't know. The polar ice caps disappear in the Martian summer, so there is not that much history of climate. Maybe someone will find something in the future.
He has further another follow-up question, whether rovers on Mars, or we can, do it in future, can attempt to figure that out.
Maybe.
Yeah.
I don't know.
There is another question by Mr. Akash Vispute. can solar cycle affect the tropospheric variability?
Well, the indicators I showed, let's go back. Here. All these indicators are for tropospheric variability. And these are reconstructions of temperature, indirect from lake sediments, but the sediments were sedimenting out from the lower troposphere, from the sea. This is in a cave in Oman where moisture was coming in at different rates. Again, that is due to rainfall changes. Ice rafted debris are telling something about the temperature in the northern Atlantic. Again, very close to the surface. This is how fast icebergs, you see one over here, how fast they melt, how far south they can go from Greenland.
Yeah, thank you. So there is a question by Dr. Vagish Mishra, who is in our panel as well. Can one expect the situations like Maunder minimum can cool the planet to reserve or significantly slow down the human-caused global warming in the coming decades? Also,
The simple answer to that, no. Cannot. These changes in temperature we have seen in the past, they're 0.2 degrees. We have already had a 1.2 degree rise in temperatures in the last 150 years, and it's continuing. Even, 0.2 degree, you're not going to notice it. It's nothing.
Okay. So he further asks, should we expect that sun has a stronger effect on the stratospheric heat budget than the tropospheric layers of the Earth's atmosphere?
That is easily possible, and yes, indeed, you do see bigger changes. The higher up you go in the atmosphere, the bigger the effect of the sun becomes. Right? So the thermosphere is totally dominated by solar shortwave radiation. In the stratosphere, there is also a bigger effect. Thermosphere, it is smaller. It's also denser, especially the UV radiation doesn't get that far down.
Yeah, thank you. Yeah. So there is a question by Mr. Bhaskar Mukherjee. Does solar wind heat Earth's atmosphere significantly?
I would be doubtful about that because the amount of energy in the solar wind is a tiny fraction of that in the radiation. The solar wind does change quite a bit between activity minimum and maximum, but I'm not sure. Nandita, you can answer that better. By how much does the energy content, the energy density of the solar wind actually change? Because you have much lower density at activity minimum, but the speeds are higher. So it goes with the square of the speed, so it's a factor of 4. I don't know. I cannot say how much the change is, but the total energy density is really tiny compared with what you have in the radiation.
Okay, thanks. There is a question by Professor Divyandu Chakravarti. We mostly talk about 11-year activity cycle or 22-year magnetic cycle. How important is the longer solar periodicities?
That is a good question. I didn't go into any longer periods in this talk. And our knowledge of the longer periods is not, is it really periodic or not? Where was I? I need to go the other way. Yeah. So this is a reconstruction here. You can sometimes, you have a certain periodicity with a period of around 70 to 100 years. It's the so-called Gleisberg cycle. but the signal is quite weak compared with the 11-year cycle. Some people see longer periods in there. There is a 200-year, there's a 1,400-year, but it's never clear. And you see that obviously not in the sunspot numbers anymore, direct measurements, but only in these carbon and 10 beryllium data. And it's never clear if these really longer periods, if they are solar or if they are of the climate system. Because one small issue with carbon-14 and beryllium-10 is that they are also, beryllium-10 more than carbon, they are also affected by the climate, by changes in ocean circulation, etc. So there is a carbon cycle playing a role here as well, which we try to take out. But if that carbon cycle is, for example, variable at a period of 1,400 years, there is no really good evidence model, whatever, for that, except what is in here. So there is always a certain level of uncertainty.
Okay, yeah, thanks. There is a question by Dr. Hariom Watts. Large variability of solar X-ray. Is it possible to see that in Earth's ionosphere?
Yeah, I mean, as I said, upper atmosphere, ionosphere, they all are strongly affected by shortwave solar radiation, and you see effects, sure.
Okay, thanks. So I can't see any further question on the chat box. So before I come to our panel, I would like to mention that some of our viewers have mentioned their association with Dr. Arvind Bhatnagar, and they have thanked him for his immense contributions. So I can see messages from Suchitra Balachandran, Parth Rawal, Shivani Bhatnagar. So yeah, thank you for watching this YouTube video. So I'll now come to our panel. So I invite my colleagues who are joining us through WebEx. I invite them for the questions, and they can interact directly to Professor Sami Solanki.
I have a question, Bhuvan.
Yeah, Professor Ambastha, yeah, please.
Yeah. I'm just curious to know whether you have extended the prediction of sunspot number back up to the last glacial maximum, and whether this correlation is visible. Whether you see a relation between the sunspot number and the surface temperature of the Earth at that time. I would also like to know whether during the Maunder minimum, the southern hemisphere also experienced cooling. I mean, we talk about cooling in Europe, but whether this was seen in the southern hemisphere as well, is it well documented? Thank you.
Yeah.
It was actually Professor D. Banerjee who was asking the question. Yeah.
Right. Yes. Yeah. No, these are good questions. So the southern hemisphere is certainly not as well documented. It is. I mean, the North Atlantic, Europe, U.S., continental U.S. These are the parts which are best studied. Europe is the best. If you go back a few hundred years, there have been many measurement series starting long ago. So we have better measurements for the southern hemisphere, a little bit less clear cut what was going on at these timescales. So the measurements that one has are for Antarctica, which are a lot more stable. They show less variations than what you see in the North Atlantic, for example. And one reason could be, one reason why Europe is so strongly affected by any changes is because the climate in Europe depends totally on the Gulf Stream. So when the Gulf Stream, which is now relatively strong, brings warm water from the Gulf of Mexico straight into Northern Europe. And if it were not there, Europe would be a very inhospitable place. And the Gulf Stream itself is relatively sensitive to external parameters, be this salinity of the oceans or changes in temperature of the waters in the Gulf Stream, other places. So one thing people are thinking why Europe reacts so strongly to external forcings is that the Gulf Stream switches on and off, becomes stronger and weaker, whereas Antarctica is less affected by such changes. What was your other question? Sorry, I've forgotten. If we reconstructed in the glacier.
LGM.
Yes. So no, we did not. And the reason is that we do not really dare to do that. Well, first of all, carbon-14, because of its half-life of 5,000-6,000 years, the noise starts to go up the further back you go. Yeah. So reconstructions just becomes very noisy, or you would have to average over huge chunks to get a reasonable signal to noise over many years. 10 beryllium is better from ice cores. But the trouble is, so carbon-14 depends on ocean circulation, that's a carbon cycle, which change. You're not exactly sure exactly how they change, but they are different during an ice age than during the Holocene, right? During such an interglacial. At some point, maybe we'll get brave enough, if there are sufficient good data, to go back into the glacial times. But so far, we have always said, okay, it's dangerous, right? You might just be producing something which is not really the sun, but basically reflecting these changes. And for beryllium-10, where the measurements are easier for the long time scales, the problem there is that it depends very much on snowfall, and you get beryllium-10 from glaciers, basically. So either Greenland or Antarctica. And if the amount of snowfall changes very much, or how much of the snow stays there, and how much there is intermixing in the atmosphere, how much of the beryllium-10 is dragged out, which is climate dependent, that people have shown in the meantime from such models. That'll give you very different results again. So again, we do not dare go back. So we are comfortable with the small climate changes we had in the Holocene, but we are not comfortable with reconstructing further back when the climate was very different, because we might just get totally wrong results.
So Solanki, do you have time to take more questions? Because I remember you told that you would have.
Yes, I have. Yeah, unfortunately, I have a meeting of the which has already started of the PIs of the Solar Orbiter mission of the various instruments. But I can take one or two more questions. Let's say 5 more minutes.
Carry on, Bhavan.
Yeah. So I think we can take a couple of questions. So I invite our panel members. So we are having very interesting discussions, but Professor Solanki has some time limitations as well. So, but still we can take 1 or 2 questions. So, so any other question? So if there are, yeah. Yeah, Professor Pallav. Yeah.
Yes, Professor Solanki, enjoy your talk very much. Thank you very much for this wonderful talk.
Thank you.
So in terms of reconstruction of the solar activity, say if you go for 4-bush decreases, it goes to some age. Then tree rings, next something, and for carbon 14 it goes further down. So so all this reconstruction that you have shown is a mixture of these and any or any other parameters that have gone into the reconstructions.
Well, there is, especially for the very long time scales, for the reconstructions based on carbon 14 or beryllium 10, we need to take into account variations of the Earth's magnetic field. As I said, the solar magnetic field is an important parameter that determines how many cosmic rays, what the flux of cosmic rays is reaching the Earth. But obviously, the Earth's magnetic field is also a major shield which keeps most of them away from the atmosphere. And on very short time scales, the Earth's magnetic field is relatively stable, but not on these very long time scales that we're talking of, right? Of centuries to millennia. So we always depend on how accurate models of the geomagnetic field are. And we always try to take the latest ones into account. And they have been changing. So that's also one of the reasons why we keep making new reconstructions to take into account that.
So I have a question. One, can I?
Yeah, sure. Yeah, please go ahead.
So you talked about the Sunrise Mission 3, and you mentioned that this would be taking some upgraded and more sensitive instruments. Is there any plan of having a coronagraph being flown
No.
in? There's no. Is it difficult or more difficult than flying the magnetograph? And that's the reason.
It's a totally separate instrument. So,
yes, of course.
Making a 1 meter telescope with a coronagraph, that is challenging. And it's not the physics we were trying to do. And we're trying to measure the magnetic field as accurately as possible with the highest resolution. For a coronagraph, you don't need that kind of resolution. It's also just because you don't have the light.
Yeah.
As far as I know, there is a Korean-US collaboration, Kasi with Goddard, I think. I'm not 100%
Yes,
sure.
Gopal Swami, I think he had flown one.
Yes. Where they are, I don't know if they have flown already.
Yeah,
I think they have
flew,
flown.
yes, last year probably.
One experiment, yeah, was flown.
Yeah. Okay, thank you.
So any other question by the panel members? So I think there are no further questions. So let me thank Professor Sami Solanki again. So now I'll hand over to my colleague, Dr. Rohan, for a vote of thanks. Rohan, please.
Yeah, thank you, Bhuvan. So on behalf of Director PRL, the Amrit Vyakyan Committee, and all my PRL colleagues, I would like to thank Professor Solanki immensely for taking the time out of his busy schedule to be amongst us and to deliver this very special colloquium. Thank you, sir. A special word of thanks to Dr. Anil Bharadwaj for his constant support and involvement in this lecture series. I would also like to thank the PRL Ka Amrit Vyakyan Committee for their constant efforts in managing and organizing the colloquium on a regular basis. Last but certainly not the least, thank you one and all for your participation in making the Vyakyan a great success. Thank you and wish you all a very good evening.
Excuse me, I would just like to thank everybody. Could I continue?
Yeah, sure. Yeah.
Actually, I would like to really thank Director PRL and all USO scientists and PRL scientists for basically going forward with this memorial lecture. It is a very, we are feeling so proud to be here with all of you today because of our dad. And we are basically, I just wanted to give you a brief profile of our family. My father was an astrophysicist, but all three daughters which he had, nobody of us went into his science. But we are three sisters and we are all in separate aspects. And it is an honor, along with my mother, who is also here. And she's also listening to the whole lecture. And she is really thankful from her. It is a heartfelt thank you from her side also to PRL, who has been the main, initiating organization behind this. I was trying to, for a long time, I was trying to make a society under his name. But I think so. This is one thing which has gone forward. Then I'll be in touch with Dr. Nandita, and I hope we can do that also. Thank you once again to PRL and all scientists there. And thank you, Dr. Solanki, for such a nice presentation. I cannot say I understood most of it, but it was a very general kind of an explanation about many things which we used to hear throughout our lifetime. So thank you once again, and from Dr. Bhatnagar's family. Thank you very much.
Thank you very much. It's been my pleasure. It's been a great pleasure to. I didn't know you would be here and that Arvind Bhatnagar's family would be listening. So it's a particular honor.
Yeah, for us also it's an honor. Thank you everyone once again. So it was a pleasure. Yeah,
thank you very much, Dr. Tripti Bhatnagar. Yeah, thank you.